In the last video, I did refer to the fact that we might be able to expand the octet in some cases. And depending on what other chemistry classes you've taken, you will occasionally find an instructor who tells you can't ever expand octets. And there's some interesting research behind this, but what we find is that for practical use, even if it's not necessarily the most accurate piece of information, drawing structures that have expanded octets give us the information that we need in order to use that bonding model and apply it to other chemistry that we want to do. So for this class, you can expand octets, but only in certain cases, and those cases are only only for elements in the third row and beyond. And the reasoning behind this is that if you're in the third row of the periodic table, you're at a principal quantum number of 3, right? That's where everything falls, that we start filling 3s, 3p, and at n equals 3, you are allowed to have d orbitals. So at n equals 3, we have access to d orbitals to hold the extra electrons. So in the last video, when I was talking about never expanding the octet for nitrogen, that's just because nitrogen is in the second row. It doesn't have access to the d orbitals. You cannot expand the octet for anything in the second row. But as soon as we get to the third row, we have the ability to do this. And the reason we will do this, so the reason we will create Lewis structures that have expanded octets, is to minimize formal charges. So like most things, this is going to be best done with an example. So let's look at ClO4 minus. My valence electrons here, 7 for chlorine, plus 4 times 6 for oxygen, plus 1 more because this has a negative charge. And I have 32 available electrons. Okay, so chlorine is in the middle. It's listed first. It's also less electronegative than oxygen. So I put chlorine in the middle, and I attach all of my oxygens with bonding pairs. I fill in my octets for the outer atoms. And 8, 16, 24, 32. I've used all of my electrons. I don't have any extra that I need to put around chlorine, but that's actually fine because chlorine has an octet. So the only thing left for me to do is calculate formal charges. And I'm going to put these in a different color just so they stand out really well. And the negative charges on all of my oxygens won't surprise you based on what their bonding looks like. But you start to get a little nervous though, right? Because this molecule has a negative charge overall. All 4 of my oxygens have negative formal charges. So you can confirm this with the actual formal charge calculation, but based on this, what we're expecting is a +3 formal charge for chlorine. These formal charges are kind of out of line. They are huge. Every atom in this molecule has a formal charge, and chlorine has a +3. Now, it's less electronegative than oxygen, but it's still a fairly electronegative atom. It's not going to be happy with a positive formal charge. So, what we can do is push electrons from the oxygens, those lone pairs, push them down and make bonding pairs, which does expand the octet of chlorine. But since chlorine is third row and beyond, we totally have the ability to do this. So I want you to do some practice. I want you to practice drawing the arrows and pushing those electrons so that you know where they came from, where they're going, and what you should end up with as a result. And this will give you a clue about where to stop. So if we push electrons down, our molecule still has an overall negative charge. So I guess you could say that you have a couple of options. If you push down every single, a lone pair from every single oxygen to chlorine, you could make 4 double bonds here. Now, if you make 4 double bonds, you do still have the correct number of electrons. There are 32. But when you go through and calculate your formal charges, I'll put this in green, what you find is that all of your oxygens are 0 and chlorine is negative. Or your other option is to only push down 3 of these and leave 1 oxygen with a single bond. You should find, if you do this, I'll do this one in orange. 3 oxygens have 0 formal charge, chlorine has 0, and this oxygen has a negative formal charge. So based on our formal charge rules, we want the negative formal charge on the more electronegative atom. So this is the best one. But when you get to this point, we have 4 oxygens that are possible. So we'll get them A, B, C, D. The way that I've drawn this, I've got the single bond between chlorine and oxygen C. Now, there's absolutely no reason that that specific oxygen is chosen to have the single bond. I could have instead drawn this with the double bonds on B, C, and D, and the single bond on A, and I would have the same types of bonds between the same types of atoms. So I would have equivalent resonance structures. So this structure is the best, but because I have a possibility of putting that single bond in any position, my real full answer here is that I'm going to start with this same structure that I already drew. Chlorine single bond in that oxygen on the right. Negative, get all my lone pairs in here. So this was one possibility, or I could have that single bond in this chlorine down here. This would get a negative. Let me make sure I have everything. So I could have the single bond between chlorine and oxygen C, chlorine and oxygen D. Next structure, it could be between chlorine and oxygen A. And last possibility, it could be between chlorine and oxygen B. When you are doing these, I very strongly recommend that you do this kind of systematic movement of electrons and make sure you're only moving electrons, right? Let's track this. This was oxygen C to the right. It's still oxygen C in that exact same position, right? The oxygen that's down is oxygen D. This is still D. None of the atoms have moved. The only thing I've done is moved the electrons around so that the single bond is potentially between chlorine and any one of the equivalent oxygens attached to it. Okay, so that's what an expanded octet would look like. The last mini topic here is about radicals. These are species that have odd numbers of electrons. And you can use all of the rules and steps to figure out which structure is the best structure. I just essentially want you to have a warning that if you have an odd number of electrons, you won't be able to pair all of them up. So you're going to have some atom that has a single electron on it, and you'll still have to pick the best Lewis structure here. But the rules that we have already will let you pick that best structure. So an example of a radical is NO, and this has 11 electrons. So when you draw the Lewis structure for this, and this is a diatomic, so we don't have a central atom, it's just nitrogen connected to oxygen, you have the possibility of making this so that oxygen has an octet and nitrogen, it doesn't quite have an octet because I ran out of electrons. What do I have? 2, 4, 6, 7 electrons around nitrogen. I can't make any other bonds, right? I can't take a lone pair and make it into a bonding pair. I can't move my single electron down because it wouldn't form a full bonding pair, right? It'd just be kind of like that single electron, so we leave it on the atom. My other option is that I could make sure that nitrogen gets the octet and put the single electron and one lone pair on oxygen. So these are the structures that I have to choose from. Now, what I haven't done yet is calculate the formal charges for these atoms in these two structures. And that's it, all you have to do. So just like every other structure, calculate the formal charges, use those formal charges to choose the best Lewis structure. So when I go through and do my formal charges, what I find is that on the structure on the left, this nitrogen with a lone pair, a single electron, and a double bond has a formal charge of 0. Oxygen is 0. In the structure on the right, this nitrogen has a negative, and this oxygen has a positive. So if I'm choosing just based on minimizing formal charges, the structure on the left is the best structure.